Today, I want to explore solids of revolution using the disk method. A solid of revolution is exactly what it sounds like it is. It is the result of rotating a region bounded by a graph or graphs about a certain axis, that is usually the x or the y axis. My hope is that over the course of the video you gain a solid understanding of the reasoning behind this method and become familiar with simple uses of the method. With that being said, let's jump into the video. However, before we get on to tackling the disk method, let's look at a more simple problem as review and to build the foundation of what is to come. Consider the following function. Let's investigate the area under this curve. Recall that we usually find the area under a function by first breaking it up into little rectangles. This is what was done here. Each of these rectangles has a width of dx and a height of f of x. As a result, this means that each of these rectangles has a small amount of area dA, where dA equals f of x times dx. The important idea is that as we let dx approach 0, these rectangles would better approximate the area under the curve. Thus, we can say that if we add up all of these little pieces of area dA, we will get the area under the curve. We do this using an integral, and we write that the area under the curve is equal to the integral of f of x dx. Now, naturally this is all very simple review, but I want to emphasize the fact that the integral symbol denotes a continuous sum of a quantity, instead of it being some abstract concept of the area under a curve. This is what gives the integral so much versatility. Here it is used to sum up the quantity of f of x times dx and gives an area as a result, but it can be used in many more places as well. With all that being said, let's now turn to tackling the disk method head on. Consider the function f of x equals x squared. Let's concentrate on the region bounded by this function and the x-axis between x equals 0 and x equals 2. What if we rotated this region around the x-axis to form a solid? What would be the volume of this resulting solid? How should we even start this problem? The key again lies in using the same principle that we used earlier on in this video to find the area under a simple function. Dividing the problem into smaller pieces which can then be added up using an integral. If we sliced up area into little rectangles, then we can slice up volume into little prisms. In the disk method, these little prisms are cylinders that are formed by slicing the region that will be rotated around the x-axis. Let's take a closer look at what this means visually. Here I am putting on the screen an approximation of the volume of the solid using cylinders. This isn't a very good approximation, but the point is that as we add more and more and more cylinders to approximate this shape, then our approximation will get better and better and better. In the limit, as the number of cylinders approaches infinity, the thickness of each cylinder approaches 0 and each cylinder becomes infinitely thin. As a result, this approximation of the volume of the solid becomes more and more accurate, and at the extreme limit we will have perfectly recreated our original shape using these cylinders. However, for now, let's return to a more crude approximation so that we can better see each individual cylinder. Assume that these cylinders are still practically infinitely thin and thus remain a good approximation for the overall volume of the solid of revolution. Let's examine how these cylinders were generated to be able to dimension and find their volumes, so that we can add them all up using an integral in the future to find the total volume of this solid of revolution. In fact, let's consider just one single cylinder and see what its dimensions are and where it comes from. To make this part easier, I'm also going to redraw the original graph of the function x squared that was revolved to form this volume. The interesting thing is that we can think of this cylinder as being formed by rotating just a small rectangular section of the original region around the x-axis. Let me show you what I mean by that. Let's examine this small rectangle with very small width that we will call dx and height f of x in the desired region that will be revolved. Now, if we revolve this little rectangle around the x-axis, we will get a small cylinder that can be used to approximate the volume of revolving the whole region around the x-axis. If we divide the area up into many little rectangles, each with very small thickness dx so that they do a good job of filling the entire region under the graph in question, and revolve each of these rectangles around the x-axis, we get a complete approximation of the volume of the region. Each little cylinder has a radius of f of x, which comes from the height of the little rectangle that revolves to form it. The cylinder also has a height of dx that comes from the thickness of the rectangle. With those facts established, we can now find the small amount of volume that we will call dV of each little cylinder. Using the formula volume equals pi r squared h for the cylinder gives a value of dV equals pi times f of x squared dx in general terms. Now, to find the total volume of the solid, let's add up all of these small amounts of volume dV along the axis of the solid of revolution for all the cylinders. To do this, let us note that we are assuming that each cylinder is infinitesimally thin, and thus there are an infinite number of them and their volumes span a continuous range of values. As a result, to add them up, we will use an integral, which denotes a continuous sum as we discussed earlier. When we integrate both sides, we find that the total volume, V, is equal to the definite integral from a to b of pi times f of x squared dx, where the bounds a and b are determined by the location of the region that we are revolving. This formula right here is known as the disk method, as the cylinders that it uses to find the volume of solids of revolution look like disks. Another important thing to recognize about this method is that it slices the region to be revolved into solids perpendicular to the axis of rotation, which is contrast with other methods that use parallel slicing. Let's look at the concrete example of f of x equals x squared to get a better feel for this formula. Recall that in this case we were rotating the region bounded by this graph and the x-axis and the line x equals 2 around the x-axis. As a result, the bounds of our integral become from x equals 0 to x equals 2. Further, our function is f of x equals x squared, so let's add that into the equation. If we simplify this, then we get the following integral. This can be evaluated using the power rule, and we get the final answer of 32 pi over 5 for the volume of this solid of revolution. And look at that, we just found the volume of a solid of revolution using the disk method. Although this method does have many other applications that are worth exploring, hopefully this video provided an insight into the basics of the method and how it came about. If you liked the video, please consider subscribing to the channel. But nonetheless, thanks for watching and I'll see you next time.